Okay, so thank you, Mari. And it's a pleasure to introduce Sylvia Wenmackers. Okay. And her talk is about radical conceptual change in physics. So, Sylvia.
Okay, thank you. Can you all hear me well?
Yes.
Okay. Good morning, and thanks for coming. Indeed, I have prepared a talk about changes in physics, which probably will involve change related to the conceptual spaces. So in this talk, I will actually start with a case study. So for the first minutes, you can still sit back and relax. It's like a story about perihelion of mercury. There was a problem with that in the 19th century, which was only solved in the 20th century. It is well known, but since I want to use this as a case study to study conceptual spaces, it may be good to rehearse it here. In relation to this case study, I was thinking of identifying the relevant conceptual spaces, and in another project, I'm actually also interested in the probabilities and how they change. But for now, of course, the focus is on the conceptual space. But as a starting point, I actually want to remain agnostic as to whether conceptual spaces are the best tool or a very good tool to do philosophy of science. That is part of what I want to explore here. Is that true? So I am completely convinced that conceptual spaces are very helpful in cognitive science, but I want to see more worked examples before I conclude that it is a good tool for philosophy of science. So that is why I thought it could be good to look at a case study and try to identify the spaces there. And a minor goal is that I want to connect various subfields, so conceptual spaces with philosophy of science and also philosophy of probability. Okay, so let's look into this case study. Well, actually, I will start with a prequel. So right before the story of Mercury, the astronomer Le Verrier looked into the movement of various planets, and he tried to apply Newtonian theory, so the gravitation of the sun, but also perturbations due to other known planets, to predict the properties of the orbits of the known planets. And there was a problem, a slight deviation from the theoretical expectation in the case of Uranus. And then Le Verrier posited that this could be due to another planet, and he even calculated at which angle this would be visible. And he sent a letter, I think it was to Berlin, so in Berlin, Gala. And the very evening when he had received that letter, he did observations and he discovered, so he confirmed experimentally that indeed very close to the predicted value there was this extra planet, which we now know as Neptune. So this was, of course, a huge success for Le Verrier, and this led him, or he was already working on this, he had a program of trying to do this for all the known planets, so work through Newtonian theory with perturbations and predict everything and unify all the known observations. This was what he was working on. Now, in the case of Mercury, it had been observed that the orbit, so usually we think of an orbit as, if you have the theory of Kepler in mind, you know if there is only the sun and one planet, it will be a perfect ellipse, and this ellipse will stay fixed in space. But it was observed in the case of Mercury that the orbit is actually moving through space, so with each pass through. And then if we look at the position of the orbit that is closest to the sun, that's called the perihelion, that will actually circle around the sun through time. And this is so the speed at which this advances is the value of interest here. And so it was measured and compared by Le Verrier to the Newtonian prediction. And there was a mismatch. So the value that they then reported was 38 arc seconds per century. So that was the anomaly, because that was the difference between the theoretical and the observed value. So the modern value is about 43 arc seconds per century. So Le Verrier had just had this huge success with discovering a planet by doing this kind of theoretical calculations. And he thought about this case, and he thought, well, also here there could be another planet between Mercury and the Sun. And it was even given a name over time. It was called Vulcan. And there were even reports of observations of this posited planet. But in this case, each time when there had been an observation, it wasn't confirmed by other observatories. Le Verrier also had other hypotheses. Maybe the Sun isn't completely round. And as late as 1906, there was someone, Seliger, who had yet another hypothesis. Maybe there is some coronal mass or extra mass, like a ring around the Sun, something like that. So there were hypotheses very similar to the previous case, but in this case it wasn't confirmed. So how this case was solved actually came from a very different angle, because meanwhile, Albert Einstein was trying to generalize his result from 1905, which we now call special relativity theory, and he wanted to include gravity. And he has probably read the book by Mach, which was one of the authors he was familiar with. And there was a hint, there was a reference to a paper, and there are also there is some evidence that he studied this paper by Gerber, in which the perihelion problem of Mercury was mentioned, and also connected to the idea of relativity somehow. And we know from a letter that at least in 1907, Einstein was working on the Mercury perihelion problem, and he thought it would be related to solving the unification of gravity with his special relativity. So also Poincaré mentioned a possible connection between relativity and the perihelion case. So in 1913, together with his former classmate Grossman, that's the person in the picture here, Einstein worked on a possible generalization of his theory, and with another of his former study friends, Bessel, they calculated what would be the effect on the precession of Mercury, and indeed there was a correction in the good direction, but it was not big enough. So this was never published. So they found an extra 18 arc seconds. There was another theory around that they checked this had a correction in the wrong direction, so that was reason to believe they were somehow on the good track, but this was one of the three reasons why Einstein left this so-called entwurf theory, so the precursor of general relativity, and looked further. So then in November 1915, he published a series of 4 papers, which ultimately, so the fourth one led him to his generally covariant field equations, so the real, what we now call the real basis of general relativity. But already in the third paper, so before his full theory was complete, he looked again at the Mercury case, and he found the correct value within the then known experimental bounds. So this really convinced him that now he had found the good theory, and there was experimental evidence already available that for him confirmed it. So if we return to the chronology, so we had this problem that was known from the 19th century. It was only solved in the 20th century, but not by any local small additional hypothesis that was then confirmed. It was really a completely new theory, which was also motivated by very other concerns than this one problem with Mercury, namely the question of how to unify the ideas of relativity theory with gravity. And if you're interested in this, there is a very recent book. It's called The Hunt for Vulcan. And the small print here says, and how Albert Einstein destroyed the planet, discovered relativity, and deciphered the universe. So that gives you the whole story in much more detail that I told you now. But so the point for to make the connection why I wanted to look into this case is that we needed here a completely different physical theory to explain this problem, and I thought this would be a radical conceptual change in physics, a good example of that. So in this talk, I tried to identify the conceptual spaces before and after the change. That's actually the main question for today. And then there is still the background question, is that a good way to represent the change and the continuity, so both sides of the question, with previous Newtonian theory? So before I do that, I wanted to add a small part about classifying theory changes, because we have heard about that concerning conceptual changes, the 5 degrees from mild to severe that we heard on the first keynote of this presentation by Peter. But there also in other contexts, people have tried to classify theory changes, so without a context of outside the context of conceptual spaces. So this is, for instance, John Ehrman in his book on Bayesianism, Bayes or Bust. And he is also talking about Kuhnian revolutions, and he makes a distinction between milder forms of theory change and the radical ones. And he says, well, in some cases, we identify new possibilities, but actually they were already in the realm of the theories we had. So we just didn't recognize them, but they were implicitly there. And when we make that more explicit, that's a mild form of change. If you are thinking about conceptual spaces, that could be related to these changes in salience. And a more radical form occurs when the space of possibilities is itself significantly altered. Of course, if you are listening with the conceptual spaces background, that could be related to adding new dimensions or new domains to a conceptual space, or also rejecting the old ones and replacing them with new ones. And for his project, he remarked that there is a problem with the usual account of Bayesianism here, because Bayesianism only tells you how to revise probabilities that you assign to possibilities you already knew. But in the history of science, at certain points, there are new possibilities that are being recognized, there are new hypotheses or theories that are being considered, and then you have to assign them a probability where they had none before because you didn't know about them. They didn't exist yet. And this is actually why he remarks that both of these cases form a problem for Bayesianism. So we heard the detailed account of how we could categorize changes to conceptual spaces 2 days ago. So this is an older fragment from the 2000 book where the connection is made to Kuhnian revolutions and the connection to theory change and the underlying conceptual spaces. So one possible way of thinking about the case study here is that whether or not we talk about an anomaly in the observation of the perihelion of Mercury, so whether we categorize that as an anomaly or not will in this case depend on whether we were working with Newtonian theory, where there is indeed an anomaly, or with new theory, general relativity, which gives you the very close to the observed value without additional hypotheses. So there you wouldn't categorize that observation as an anomaly. I'll skip over this more quickly because we have heard this in more detail actually already. And so I was thinking about this in terms of the theories involved, the scientific theories, there may be changes. Maybe we have to model that as changes in conceptual spaces. Now, those theories, so for instance, Newtonian theory and Einstein's general relativity theory, they will give us predictions concerning certain variables that we can measure. These variables are typically not fundamental values here. So for instance, how much the perihelion of a particular planet advances for a given point in time, span of time, that is not a fundamental value. That's not one of the axes in the conceptual space in either theory. But it is something you can compute with it. And you can actually compute it for both theories. So it seems that there is another space involved here, which you could call the evidence space or the sample space, and which is also what you need if you want to form a statistical hypothesis. You will need a sample space and actually an algebra over that. So it may also be that there are changes there, that at some point you discover there is such a thing as a magnetic field and you have to make changes to the very things you are measuring. But that was not the case in the case study I have picked here. And then we might think there is yet another space which is usually not made explicit, but which you are forced to think about if you are assigning probabilities and thinking in a Bayesian framework. And that is, what is the space of hypotheses which forces you to assign likelihoods to the evidence space, associated with the evidence space. So actually, when there are spaces that change, it may be either one of the three or maybe a combination thereof. And so in relation to the problem there is in Bayesianism, when these new possibilities arise, it's actually in this space that the problem occurs. So there are new hypotheses that are being formulated. And one suggestion that has been made to solve that is to sort of reserve a place for hypotheses that will be formulated later on. This is called a catch-all. It was an idea of Chimney. It is mentioned, but mostly criticized by Ehrman. But I do think we can use it to solve this part of the problem. And this is what we focused on in a paper in Synthese that I wrote together with Jan-Willem Romein, so a new theory for old evidence. But that is, I just wanted to make that clear, that is about this space. And this space, the conceptual space of the underlying scientific theory, isn't much in view in that paper. And that is what I wanted to focus on now. So changes in one part of this three-part structure may lead to changes elsewhere. And then I was thinking, like, what are the possible changes that we might have? So if we're thinking about the sample space, so the kind which gives you the kind of data you might get. So you have a certain set called omega, and you have a partition on it. So omega could be positions, for instance, and the partition on it, so the algebra actually, will give you, it will clump together certain possibilities. So that you can think of that as being related to the fact that you cannot measure anything perfectly. There will always be a region of possibilities that you cannot exclude with any measurement. Now, if you make changes to that algebra, then I would classify that as the mildest possible change, because this is just, it was already in the scope of the theory, but you are now making it more explicit. So, and even if you try to change the algebra completely, I think this can be reconstructed as a mild form of change. Now, in some cases, you might want to extend the possible values. So, values that you hadn't deemed possible before, you may want to add that. Well, if you think about a change like this, so when you extend the range of possibilities, if you think about that in the context of conceptual space, it's just that it's still the same dimensions, it's just another range. So even that is quite mild. So a more radical case is when you add a dimension. But if you think about that probabilistically, it may be that this extra dimension, at least for some measurements, is statistically independent. So in that case, it is, again, not that severe, not as severe as it could be. In some cases, you might want to reconsider certain options and fine-grain them. So it's like adding a variable that can be reconstructed as there was a hidden variable beforehand. That's still not the most radical change. So the more radical ones, I think, are the ones where you add a dimension, and it's not just statistically independent. It really adds new structure to the kind of measurements you can obtain. And the most radical one I could imagine is actually one where the new space and the old space they are not part of each other, but maybe they are related by a projection or something like that. And this is what I was thinking of in the case of classical limits. It's not that the old theory is a part of the new theory. It strictly falls within the new theory, except in certain limits, but those are unphysical limits. For instance, setting the speed of light to infinity. We know it's not, so it's not part of the new theory, but there is an interesting relation. But in terms of conceptual spaces, this becomes very complicated because there is like an external relation to the two spaces. It's not in any of the spaces, but there is an external relation between the two, which can be very complicated. Now, in this drawing, it's actually a bit misleading because I started with omega, and I had in mind the sample space, so the things you can actually measure, the kind of data you can get. And in the case study, these data are related to under which angles we see a planet, and we record that over time, and from that we compute the perihelion advance. So that is actually a commenting to the old theory and the new theory. So then we are indeed talking about omega, but there is a shared space of possibilities. But the thing I'm depicting here symbolically, so the idea of a classical limit, is not about the measured values, but it's really about the values that you use in the theory to compute that shared number. So this would be the underlying conceptual space, but that doesn't necessarily mean that something as radical as that is happening to the evidence space. So although I'm always using the symbol omega, this classification is actually more broad and can be between any of the two spaces that I mentioned here. So the conceptual space underlying the scientific theory, the space of the actual measurements, and the hypothesis space. And in any case, when we're talking about the case study, this is not about the measured values, not about the evidence space, but it could be about the conceptual space of the scientific theory. Okay, so what I have been announcing that I would like to do, I will start looking into that now. So again, in the 2000s book, there was a very good example of how a quality dimension could be introduced by physics, and that was the distinction Newton made between mass and weight. So for a physicist who has learned Newtonian mechanics, contemporary version, weight is just a force like any other one. Mass is a value that is assigned to a particle or an object, and that doesn't change depending on where it is located. And that is indeed a big change to how the word weight was used before. Now, there also was a suggestion of what the conceptual space of Newtonian particle mechanics could be for one particle. But I thought this wasn't correct because we see here the position, the time, the mass, the force. Indeed, these are the kind of things you need to know if you want to solve a textbook problem. But it seemed to me that there is something missing here, especially with the additional sentence that I quoted afterwards, once a particle has been assigned a value for all these 8 dimensions, it is fully described as far as Newtonian mechanics is concerned. So first of all, it's not perfectly clear to me how to interpret the dimensions. Does it mean we are given a position at each point in time, or are we given a point in time, a position, mass, a force? I think I have to interpret it in that way. But then velocity is missing. So we need actually an extra vector, which is again in this space, so another 3 dimensions. If we interpret time as being known at all, so that all the other values are known at all times, then we don't need all of this. Then we could just say we need all the positions at all times. And if we have a particle moving and it's not just gravitational force which is pointed downward or something like that, we actually need a force field. So we have to know it at each future position that it could be in. So I had two difficulties with that. One is how to interpret this exactly, like what I already mentioned. Is it still 8-dimensional if we need to know any of these other values at all times, or is that actually a higher dimensional thing? If we're working with fields, you could also argue that it's actually an infinitely dimensional object or space, because you need to allow that the force could be anything at any point in these 3 spatial dimensions, and it can change over time. So, yeah, I wasn't completely convinced. I closed the book and I tried to start from scratch. Thought, which spaces do you use if you do physics? Well, the obvious one you always have at some point is coordinate space. These are just the positions. If you're not talking about a point particle, actually you also need information about how an object is oriented. So in that case, one object will give you 6 dimensions, so a rigid body. But usually we're working with point particles, and then we need to specify the coordinates 3 times the number of particles. Nothing too new there. But in physics, we also use something called configuration space. And there we start from the coordinates we need, but there can be constraints on how a particle can move. For instance, if I keep this with me and I behave as a rigid body, then this extra object has no additional degrees of freedom because it's completely constrained by me. So if you then want to describe the system consisting of me, the number of coordinates would be 6. Additional this, well, there is nothing additional, really. So coordinate space would have a doubling in coordinates, but if you take into account the restraints, you would subtract them again, and it would still be 6 degrees of freedom, for instance. If you have a pendulum, and it's only able to move the mass attached to it in one plane, there's actually only 1 degree of freedom, even though you think of it as a 3-dimensional setup. So that is configuration space. And here we use the notation Q for whatever coordinates we are using. It could be, for instance, for a pendulum, it will be an angle typically. It could also be another coordinate. And then one that is used in many branches of physics as well, it's called the Facespace. There, for each particle, you will specify the position, so 3 vector, and a momentum. So we will have 6 times the number of particles dimensions. And this Facespace is used in various branches of physics. You may also know the word from thermodynamics. So if you specify the positions and the momenta of each single particle, you could be doing statistical mechanics. But at some points, when n is very large, some coarse graining may occur. And then you might be working with a much lower dimensional space, which specifies pressure, maybe entropy, temperature. You can see what's relevant for the problem at hand. So you will have a lower dimensional space because you are coarse graining. And this would still be called a phase space. But typically, by phase space, we mean that the positions and the momenta of all the particles are specified. So a fine-grained phase space. Now, at this point, so I just mentioned some spaces that are actually used in classical physics and sometimes also in modern physics. But it's not, I haven't argued yet that any of these is a conceptual space or a domain of a conceptual space. But if I have to pick from these options, I do think the phase space is the most likely to be at least a domain of the conceptual space. I talked about this part of my talk with my partner, Danny, who is also a physicist. And he said, maybe you can show an example from galactic physics. I thought, that's a good idea. So he remembered that from a course he took. So I looked for a contemporary example. So the phase space is used, for instance, to simulate the orbits of orbits, and they try to use them to explain the general shape of a galaxy using. So you're following one mass in time, and you treat all the other masses as a sort of a mean field as a background. Now, in this case, the example that I first found, I realized later, actually they are looking at two spatial dimensions. So in this case, they're looking at cross-sections that are in the spatial dimensions, but there are similar plots to be found also in the literature on chaotic systems and things like that, where one of the axes will actually be one of the momentum parts. So this is indeed a space that is used in physics, but it isn't clear up front whether now this is a conceptual space or not. It is very useful to compute things and to visualize things. But I do think there are reasons for caution here. So if I would say that the phase space is the conceptual space of Newtonian mechanics, I think there is something misleading about that claim. Think about the case study. So when we move from Newtonian theory to Newtonian theory with an additional hypothesis of there being an extra planet, we increase the number of bodies, the number of masses, with 1. But for the phase space, that would mean that we actually add 7 dimensions. So it would seem to be quite a change to the conceptual space, but it's still the same theory. And if you would ask a physicist, like, is adding this hypothesis to Newtonian theory a conceptual change for you? They would say no. So there seems to be a mismatch, at least with how the word would be used intuitively, conceptual change, and what is happening here to the conceptual change. So to be clear, the phase space isn't used to represent Newtonian theory or another theory, but it is used to represent a specific system that is described with that theory. So if you have another system, then n may be different and the number of dimensions may be different. To me, that's when I was thinking about that suggested that actually there may be another conceptual space which isn't made explicit, but that trained physicists will be able to use somehow, and that is a space where you vary, for instance, the number of n, the number of particles. And I do think physicists can have, by their training, some kind of similarity judgments. Like, for some cases, it will be exactly solvable. From that number of masses on, it's not analytically solvable, so it's very different. They will make judgments like that. Also, if you have a certain number of particles, then you can change the masses a little bit, and in some cases that will make very little difference for the final results. In other cases, though, for instance, in chaotic systems, it may make a huge difference, even if you change the masses only slightly. So I was thinking that maybe the relevant conceptual space here is not the one that is being used explicitly, but there is this other space that specifies the variables that you need to set up the phase space in the first place. Maybe that is the one that is, I don't know, I haven't decided yet, but that's just a suggestion. Another thought I had related to this is, for instance, the concept of an orbit. So physicists will have some kind of classification of orbits. Some are very eccentric. In some cases, there is a trajectory, but not an orbit, because there's nothing repetitive about it. So within a phase space, you can look at orbits, but it seems that the concept orbit itself doesn't live, it isn't attached to that phase space. It's a more general concept. So maybe also there could be a space that classifies orbits that is usually not made explicit. It's used implicitly. That could be relevant to add. Yeah, maybe I'll skip over this. Okay, so those were some thoughts about Newtonian theory. Probably phase space is a good idea. There may be some additional dimensions that we have to add, for instance, the number of particles. Okay, then when we move to the, back to the case, it was ultimately solved by general relativity theory, but obviously it will be difficult to make the step at once. And also historically, that's not how it happened. In between, special relativity theory had been developed, and Minkowski had given this four-dimensional space-time formulation of it that is now the way this is actually taught. So this is also mentioned in the 2000 book already, that we had 3 spatial dimensions, 1 temporal dimension. They were separable, but they became so intrinsically linked that it's not possible to treat them as separable anymore. There are 4 integral dimensions. Now, once we have seen a theory like that, of course, we could represent Newtonian theory using a 4-dimensional space-time, and indeed, the time dimension will be a separable one. So this is what it would look like. But I thought maybe this is relevant to make explicit, because once you have the new theory and the associated conceptual space, it may allow you to reconstruct the older theory in a way that makes the change as small as possible. So as far as I know, no one ever made pictures like this before Einstein's special relativity theory was developed. But it's very natural now to think of Newtonian theory in a way like this. But reconstructions like that may make it actually harder from a hindsight perspective to appreciate how radical change may have been. So I don't know how general this remark is, but at least in this case, I thought it may be relevant. There have also been further developments of Newtonian theory after special relativity has been developed. Actually, there was a slight worry about the Newtonian approach. It's very important to have absolute accelerations in Newtonian theory, because they determine which are the real forces and which are pseudo forces, which are the inertial frames, and so on. But the way it was originally done, there are actually also absolute velocities. And there is no use for absolute velocities in the ontology or the ideas behind Newtonian theory. So there was actually a later development by Cartan, who also used a 4-dimensional structure, but not the obvious one that was depicted here. So I can't go into the details, but this came up when I was teaching the course on philosophy of time. I didn't know about it before that. But I find it very interesting that someone was able to use a 4-dimensional space-time to actually improve, in a sense, Newtonian theory. So the space-time ID is retained in general relativity. So all the relevant vectors will be 4 vectors. But there is something additional. So these field equations, they make use of field tensors. So that means they assign a tensor to each point in space-time. And here again, I think it may be argued that this is actually an infinitely dimensional object, because it can, for each point in space, it could have been assigned another value. So the possible values you can associate with a field tensor is actually an infinitely dimensional space. Now this may sound unusual, but this reminded me actually of the case in quantum mechanics. This is not, we don't need to look into quantum mechanics for the case study, but just the observation that we have an infinitely dimensional space reminded me of the complex Hilbert space that we use. Well, when we are teaching it, we usually start with the spin of an electron, because that is a 2-dimensional Hilbert space. But almost in any other case, it will be an infinitely dimensional space. So if you want to be able to describe position measurements or anything else that has a continuous range, the space that describes the pure states of a quantum system will also be infinitely dimensional. So in both cases, so both in general relativity theory and in at least in the usual framework for quantum mechanics, this is the case. But there are various formulations of the theory, and the conceptual space is also different in each case. So this may actually be another project to look into that in more detail, but I haven't done that. Now. So then I was thinking, well, what about Facespace for general relativity? So in the Newtonian case, we had the 3 spatial dimensions, and then 3 for the momentum and time, so 7. Can we do something similar with space-time? So then 4 plus 4 for locations in space-time and associated momenta. And I found that there are research projects on that, and they're actually related to the quest for a theory of quantum gravity, so the unification of quantum theory and general relativity theory. I found a paper by 3 authors. The last one is Smolin, and he thinks that we really need to go to an 8-dimensional phase space to find the theory of quantum gravity. And another theoretical physicist commented on that we will have to somehow. So this sounds very plausible, because when you describe measurements in quantum mechanics, there are certain connections between position and momentum via the uncertainty principle. So we have to make it all inseparable. So these would be 8 integral dimensions. So that was what I found before I came here. And then on the first day, I heard about a paper by Masseton, and I looked into that in the evening. And I saw that actually he makes the very same suggestion. I didn't check actually the citations he has there, but he also mentions that using such an 8-dimensional phase space is at the cutting edge research in theoretical physics at the moment for a formulation of general relativity. So we converged completely on that part. So this is a remark I already made. So despite the very different concepts used in both theories, the observational data are still are shared. So that didn't change. We are, both before and after the change, the data sets you could be looking at would be the same for the planets, how their apparent positions are, then how you compute where their actual position is in physical space. Only if you want to predict them or repredict them, you will be using a different theory. In this case, the evidence space, if you really want to make it minimal, it's at least three-dimensional, so the apparent position can be measured by 2 coordinates, and we do that through time, so we have at least 3 dimensions. So I do think that we could think of this as yet another conceptual space, like what kind of data could I have? Scientists could reason about that. And this will be what you need if you want to do an analysis in terms of probability as the sample space. So maybe we need to look into that as well. I had a few more slides, but I think I will skip the part about probabilities, and I will just go to the concluding remarks for the sake of time. It's not that many, but okay. So just to rehearse some of the points I made through the talk. So obviously in physics, there are a lot of sometimes high-dimensional spaces used explicitly. I don't think we have to think necessarily of all of them, or maybe any of them, as conceptual spaces. But at this point, I would think that the phase space, knowing that it's of a system in a particular theory, is a good candidate. Maybe there are associated dimensions, such that you can connect various phase spaces together, across theories maybe, in any case across number of particles that you want to study. And then I think maybe, just like it was the case in cognitive science, it may be the case that the most relevant conceptual spaces may be implicit. So the way scientists reason about systems, that can be across theories. And then a suggestion would be to, and actually part of the teaching is done that way, that you think of a certain target system, for instance, the solar system, and you try to model it in various theories and their associated conceptual spaces there. But then the thing you are tracking is one system, so that part is fixed. And then what you are varying are the theories, and you sort of see how that influences certain measurable properties. Yeah, that was what I had prepared for you. Thank you for your attention.
So thank you very much, Sylvia, for this talk.
Yeah, thank you very much. I mean, this was very clarifying for me. When I wrote the book, I didn't think very much about the physical details, and you're right in pointing out that the description is incomplete. Given your description, I would think that I thought that the trajectory was part of the description, so in the 8-dimensional thing. So it's not only a single point, and then you will get the 8 dimensions. And that brings me to your distinction between your analogy with phase space. And now you made it very clear to me that there is a distinction to be made between phase space and conceptual spaces. As you pointed out, I mean, a phase space has a number of values for each particle or object in the system. But the underlying conceptual spaces, what are the unifying dimensions, so to speak, for all of them. So that's, but I mean, you made this very clear. So I think that we should make that distinction very clearly in the future. And finally, the third thing I want to say is your requirement for a field. There is a simple trick you can do to turn a field into a conceptual space. I mean, if you have a force field with 3 position variables and 3 force variables, you can call this a 6-dimensional conceptual space, but then require that the force at each point is a function of the location. So you add the assumption. So it's a simple trick, but it's just instead of, as you saying, have it as an infinity, especially an infinity number, infinite number of dimensions, you simply make it a 6-dimensional space and say it's a function on a 6-dimensional space. That's a figure.
Yeah.
It's a very simple trick, but it's a way of getting around the problem.
Yeah, thank you. I think that may help to talk about it. But then, of course, I would be tempted to also try to model what kind of functions are allowed, and that we still have an infinite dimension.
Yes.
But it would make it clearer, and I think it does clear up some of the confusion I ran into. If you separate it like that, it would be clearer. So thanks for that suggestion.
Are there other questions, comments?
This may be a unfair question, but in your conclusions you say that there may be relevant conceptual spaces behind the theory. Does it imply that there are implicit assumptions in the theory, and is this means somehow to evaluate or look at the theory from a critical standpoint?
Okay, that wasn't how I was thinking about it, but maybe if I have more time, I could think about it. So I can just explain what I had in mind. So there are these various things that you have to have specified before you can build the space. And those things are in a way explicit, but they are usually not depicted as dimensions of a space. That part is explicit. Is implicit, sorry. So this would give rise to a higher dimensional thing that would be more similar, I think, to the kind of psychological dimensions that were identified for color and things like that. And that would be sort of in the head of the physicist, like in the background, not made explicit on paper when they write the article. So that was what I had in mind. Implicit assumptions in the theory, well, there will be, and there are, sometimes they come in as certain implicit ontological commitments. And I do think it could be possible to study that with the help of conceptual spaces, but I haven't done that, so I don't have any concrete example of that. Thank you.
Other questions, comments?
Yes, thanks so much. Maybe two things that are unrelated. First, on the Perihelion case. So the fact that Neptune was observed sort of close to where it was predicted. There's an alternative history to that says, look, that guy wanted to make a show. He was lucky, yeah, but he made more out of it. And so I'm not sure whether the book you pointed out, it's maybe not as much of a success story as we tend to believe. Although what you give us is that's the normal history of it. Yeah. The other remark is so in these later papers we try to say that the conceptual space can be used to reconstruct the scientific conceptual framework into which empirical theories are embedded. So that's your distinction between these two spaces that you have.
Yeah.
So the one that gives the concepts we work with, and the other is, well, what we put these concepts to work.
Yeah. So,
okay.
You want me to follow up, or you want to?
Because I thought this was, at some point, you were going from one to the other. So I think we have a clear distinction that we can make by speaking of scientific conceptual frameworks.
Okay, yeah.
In contrast to theories.
Yeah, so what I tried to do, so I tried so I did mention the Macedon paper, but actually I prepared this before I read that. And I had the feeling at some points that it was very difficult not to bring in equations and go to the symbolic level. So my impression was really that so I didn't mention it now, but there is a lot of work to be done as well. So I do think it's very hard to say anything about this connection if you're not somehow allowed or allow yourself to go via the equations and how they are related. So that was my experience with trying to think about it. But I am not claiming that you didn't make the distinction. I was just trying to think of it straight from the 2000 book and then try to apply it. And I reported some of the problems I ran into. That's.
I think we've addressed some of these things in the middle.
Okay, thanks.
Great, thank you, Fred. there other questions? Okay. Peter, yes.
Just a small comment again. Thank you for bringing up the concept of an orbit, because as I mentioned yesterday, or the day before yesterday, I said that convexity doesn't play very much of a role in physics, but now you gave me an example of a concept lab where you can talk about convexity.
Yeah, that was actually one of the things I was trying to
That's right. And then once you open my mind, I mean, we can probably find many more concepts like this.
Yeah, I guess so. Yeah.
And then a small remark on the convexity of orbit. I mean, in Newtonian case, it's trivial. But one thing is that in relativity theory, the meaning somehow of an orbit is different because it's dependent on the different. So even if the observation on data is the same, the meaning of the notion is it's a little bit like the change of mass.
Yeah, I agree. It's not exactly the same concept across theories. Yeah, I agree. Thank you.
Okay, well, let's thank again Sylvia.